Well, of course, I'm very happy to be here, and I get to Cape Town. It seems a lot these days. It's one of my favorite, fast becoming one of my favorite places. So I wanted to give you an introduction to supersymmetry. Now, supersymmetry is a subject that basically got its start in two very different ways. In the West, in Europe and the United States and the Western world, because there was still a Cold War going on, in the West, supersymmetry started with a discovery by two physicists named Vest and Zimino. And those of us in the supersymmetry business often call it SUSY, so it's not a girl. They didn't go discover a girl. They discovered supersymmetry. And this, as I said, occurs around someplace like 72 to 3. Now, independently of that, the ideas of supersymmetry had actually been discovered in Russia before then. But because there was this Cold War, which impeded the exchange of information, nobody in the West knew about it. And so two Russian physicists, Golfon, there's some kind of accent there, and Lichtman, K-I-K-H-T-M-A-N, discovered SUSY in Russia around 1968 to, say, 70. So it actually precedes the discovery of supersymmetry in the West. And so this is where this topic has come from. And supersymmetry also is a very weird topic in lots of ways. But one of the weirdest topics, ways in which supersymmetry is weird, it is both the child of string theory and the parent of superstring theory. Because, in fact, what happened is that the people who discovered supersymmetry were, in fact, working on strings. And in string theory, they found these very strange kinds of transformations that no one had ever considered before. And so they said, well, let's see if we can reproduce these kinds of properties outside of the context of string theory, but in ordinary field theory, which is the tool that, of course, the standard model is based on. So that's how supersymmetry was actually discovered, was by looking at strings and looking at the bosonic string and finding this weird set of transformations. And what's really striking about these transformations, and we're going to see why this is true, is that the supersymmetry transformations, among all of the transformations that we use in physics, are the only ones that represent where you say the change in a boson is dependent on a fermion. That's the distinctive thing about supersymmetry. So it's characteristic of supersymmetry. Throughout our talk, we're going to be using the symbol delta a lot. And the way that we use delta, it basically means the change in something, or the variation, technically. So colloquially, we can say the change in some mathematical entity or quantity. Oops, I'm losing my eraser here. So among all, if you look at the standard model, it has lots of symmetries. So supersymmetry, by the way, we use delta Q for SUSY. This is the SUSY change. So when you see delta with a Q, it means we're making a supersymmetry change in something. Now, there are lots of other sorts of changes that you can make, and those have been the topic of several sets of discussions that have gone on here. Those were the topics of the talks given by Professor Z when he was starting to do standard model. Those sit under the talks that Robert is giving on group theory, because all of these have these changes in them. But all of the other symmetries, which we can call ordinary symmetries, so I'll just say ordinary. If you look at all ordinary symmetries, they have the following property. The change in a boson is proportional to a boson. Now, it might be another boson. It might not be the same boson that the change is proportional, but it's another boson. the change of an ordinary symmetry of a fermion is proportional to a fermion. And again, it need not be the same fermion. If you have a theory with several fermions, perhaps the change of one fermion is proportional to another fermion. But the point is that fermions are going into fermions, bosons are being changed into bosons, but bosons are not changed into fermions under ordinary symmetries, and fermions are not changed into bosons under ordinary symmetries. And that's what's characteristic about supersymmetry. So for ordinary symmetries, you have those properties, but for supersymmetry, you have delta Q of a boson is proportional to a fermion. A very weird kind of idea, as we will see. And the change in a fermion is proportional to a boson. So that's sort of at the most fundamental level, if someone asks you about supersymmetry, that's one of the defining properties. That when you look at the change in the fields in the theory, the objects are changing statistics across those equal signs. You go from bosons to fermions. Now, there's another defining characteristic of supersymmetry. And this other characteristic of supersymmetry comes about as follows. And again, this touches so well on the discussions that Robert has been having and also with Tony. So let me talk a little bit about a very special kind of change, and that's translations. What do we mean when we say translation? What's a translation? That's a translation. A translation simply means to move along a direction. Now, you can take tiny steps, so you can have small translations, or I can take big, long steps and have big translations. Translations are simply straight line motions. And so, that's what translations are. They're motions along a line. At the most primitive level, this will suffice for definition. Now let's see what this actually does for us. Suppose that we have some function of x. Then, what does it mean to translate this function by a meters? Well, if the initial location, I'm going to use the symbol t for translation. That means the act of making something translate. So suppose I want to translate the field through a distance a. What does that actually do to the function? Well, if the original function is at position x, and you translate the x-axis by the number a, then the function must be evaluated at x plus a. That's what we mean by a translation. You took the measuring line and you translate it, right? Simple definition of translation. Now that we know what a translation is, let's talk about a very special class of translations. Suppose that we look at translations that are infinitesimal. Now, what does that mean to say that the translation is infinitesimal? It's a statement about the size of this number, right? If you say that something is moved infinitesimally, you're saying that this thing is something that is incredibly small. Maybe it's 1 over 10 billion, or 1 over 10 to the 10 power, or 10 to the 110 power. It's a very small number. Now, if a is very small, but we'll consider it positive for the moment, for simplicity's sake. If a is small but positive, then there's a very famous theorem here that tells us how to evaluate this. What would that be? Taylor's theorem. Taylor's theorem tells you how to write something as an expansion in this parameter. So under a translation, under an infinitesimal translation, and now I'm going to change notation on you. I'm going to write this as delta t of A. And the t means it started out as a translation, but now because I'm making it an infinitesimal translation, it makes a change occur. And so delta t of A of f means take this thing and use Taylor's theorem. Well, that gives us, Taylor's theorem says if you expand about A, the leading term occurs at A equals 0. Then there is a term that is proportional to A times the derivative of f of x, I'm using straight derivatives here, evaluated at A equal to 0. Right? And now, because A is an infinitesimal, I stop this entire series. That's the end of the series. Because for an infinitesimal quantity, part of the definition of an infinitesimal is that when you square it, you get 0. And the next term in this Taylor series is A squared. So now I have figured out what the infinitesimal change of a function is. The infinitesimal translation of a function is just A, I'm sorry. Let me try this again. I made a terrible error here. Let's straighten this up. What I really want is the following, to note that that t of A, let me write it like this, a delta of t of A of f of x is just this leading term. That's the change. The change means you look at the thing how the function changes from what it used to be. So you have to subtract off the leading term in the Taylor series. So it's just this. And now I can give you the second defining property of supersymmetry. What supersymmetry says is the following. That if you suppose you start off with a boson, some boson, any boson. If you apply the first supersymmetry variation, by the way, I should notice that in writing this change, there was an infinitesimal parameter that tells us how far we made the change. In order to talk about supersymmetry, we also have to introduce such parameters. So if I have a supersymmetry transformation, there is some infinitesimal that tells me how much I made that. It's the thing that plays the role of the A. Okay? So when I make this variation of a boson, I'm going to get something that's linear in epsilon times a fermion. That's what our first property of supersymmetry said. Now, I can make a second supersymmetry transformation. But it doesn't have to be with the same infinitesimal. It could be with a different infinitesimal parameter. So I can make a second supersymmetry transformation with an infinitesimal parameter eta. Yes?
Just to go back one line, your change with your translation of x equals a df by dx, is it a equals 0 or x evaluated?
It's evaluated at a equals to 0.
But a is greater than 0.
That was for the purposes of taking the Taylor series expansion. If you actually take the Taylor series expansion, this thing that's left over here must be independent of A. This is Taylor-Maclaurin. It's not Taylor. It's Taylor-Maclaurin that I'm using, if you want to make that specific. Okay. Yes, Robert? Oh, okay. So I can perform a second supersymmetry transformation on the transformed object. So that looks like this. And now, that means that I have epsilon. Well, epsilon was an infinitesimal parameter. It's like an angle. So it doesn't change, but you do have to change this fermion. And according to our rules, when you make a supersymmetry variation of a fermion, it turns back into a boson. So this is, if we apply delta Q of the fermion here, that's going to be something proportional to eta, because it's always going to be linear in the changing parameter, times a boson. And now I can give you the second defining property of supersymmetry. In fact, it's the most important defining property. Here I took the two supersymmetry variations in a particular order. Let me consider them consider the following set of actions. So let me do this. First, do the calculation that I just did for you, and then do the calculation, but in the opposite order. On this boson, and if this is supersymmetry, the answer turns out to be this is proportional to the infinitesimal translation with the parameter a, and a is a function linear in a and linear in epsilon. Yes, sir?
Now, I have a physical understanding. If you're changing something ordinary, if you're not taking a supersymmetric change, what does it mean physically?
Well, first of all, I haven't really defined for you the change. All I'm doing is laying out the conceptual framework that we're going to be building on. This is the mathematical general concept. I have yet to tell you how I'm going to accomplish this, but I want you to have a clear idea where we're going. Yes, ma'am?
So, if you take the boson and you turn it into a fermion and that the boson moves,
Say again?
so delta T is a translation.
Yes! That's what this equation effectively says. Effectively. And sort of, we'll make it very precise when we write the equations, but that's what this says. Now, this equation, which is very interesting. And like I said, a turns out to be a linear function in both eta and epsilon. This equation must be true not only on the boson, it must also be true for the fermion. And in particular, you do the same set of calculations on a fermion. So start with some fermion, something that's you can think of an electron or some boson like fermion or a quark or whatever your favorite fermion might be, and do the same set of operations. So you take this and then you take it in the opposite order. You apply it to your favorite fermion. And if it's supersymmetry, it's got to be proportional to a translation of A acting on that fermion. And the A here must be determined by the same function that occurs there. So that's the fundamental definition of supersymmetry. Now, we need to try to realize this idea in a real mathematical context, because all I've done is give you the broad overview of what people mean when they say supersymmetry. It's a symmetry that has this property that turns fermions into bosons, and when you calculate the commutator, and we've seen this word before, because if you remember, when you take the effect of two transformations successively and then interchange their order with a minus sign, that's called the commutator. So the point is that the commutator of two supersymmetry transformations is a ordinary space-time translation. That's the way it works. So, everyone, question? Yes?
So, the difference that you made there, it means that the change in supersymmetry is not commutative?
That's correct. But we'll have to see exactly what it is when I realize it. It's not indeed commutative. It's going to be something different. Okay, so now to try to make this a little bit more concrete. When I'm fortunate to follow Robert's lecture this morning because he introduced you to the notion of the idea of generators of symmetries. These were the things whose exponential maps led back to, in his case, orthogonal groups. So there's these things that you exponentiate to get the matrices that actually do the turning. Generators exist for this kind of construct. And in fact, in order to realize this mathematically, you must introduce a quantity we call Q alpha. It's called the supersymmetry charge. Notice it has a label, just as Robert's been, and a number of our our speakers have been doing. You attach subscripts to things, and that means that there's lots of them. You have to count the number of things here. And in a moment, I'm going to say how many there are of these things, but you have to count them. There's more than one. So first you have to introduce these objects. You also have to introduce the generator of translations. Now, what in the world would that be? Well, if you look very carefully back at my argument about how to realize an infinitesimal translation, what you ought to realize is that the derivative itself is the generator of translations. ddx is the generator of translations. So let me do the following. I'm going to introduce an object that I'm going to call P, and I'm going to define it to be I times ddx. Well, why in the world would I want to introduce a stupid I there? Well, there's this little subject called quantum mechanics. And in quantum mechanics, we know, in fact, that the generator of translations, if you go back and look in your quantum mechanics books, and you look at Schrodinger's equation, what Schrodinger tells you basically is that the momentum generator that you use in quantum mechanics is, well, let me put a minus sign here so it will be more similar, that the momentum generator in all of your quantum mechanics books is h bar over I, and if you're in a world where there's only one coordinate, not three, you write this. And so, in fact, ddx, by definition, is the generator of translations. One way to think about derivatives, what derivatives do, is if you think about functions, well, I like to think about multidimensional functions, so that's some kind of a surface, like, imagine like a sheet of paper. And so on a sheet of paper, you can tell someone the location of a single point. That takes two numbers. So you got coordinates on the paper. So coordinates tell you where you are, and now suppose you want to move away from that point. The derivatives with respect to those coordinates are what move you away from that point along the axes that you define by your coordinates. So derivatives are, by definition, little things that push points along. They push functions. So now, to be more clear on where we're going, we write the following interesting statement. We say that the commutator of epsilon alpha, and this is that parameter that remember I said it had to depend on some infinitesimal parameter? Well, this is the infinitesimal parameter. You have to introduce a number of them, not just a single one. That's the last part of my discussion was simply schematic. It wasn't a realization, but we write this commutated with eta beta q beta, and now it's a real commutator, is equal to gamma, and now I'm going to go multidimensional because this was P in the case of a world with only one direction. In our three-dimensional world, all our books on Schrodinger's equation tell us that P is actually h bar over I times the gradient. And now, remember, the way that we've been doing things in the school, we don't write arrows on things. We put indices on things when there's lots of them. So, in fact, instead of writing P this way, I can write P like d by dx. So, again, we're in this business of using subscripts. That's part of our game. If you're doing modern fundamental physics, you're going to get driven to this. Okay, so now I can finish a statement. The statement is that this closes like this. This is the rigorous mathematical definition of supersymmetry. You have to have some kind of a generator that when you multiply by the same number of parameters as there are generators, and then do it in opposite order, it generates a translation on all bosons and all fermions. Yes, sir?
A supersymmetry operator with the translation operator.
Ah, wonderful question. The question was, well, now since we're off into this abstract world of generators, what would happen if I calculate the commutator of Q alpha with an arbitrary translation? Now, if I'm making an arbitrary translation, the A that I talked about in my one-dimensional case has now got to be a vector because I could translate in the x direction, or I could do the y direction, or I could do the z direction. So I have to put an index on the A that was there before, and now write the generator of translations, which from quantum mechanics we're comfortable thinking about as P. So, question was, what's that? Answer, it's 0. At least, there's a caveat here. We have to worry about, yes, sir.
The equation you highlighted was the commutator.
I'm sorry, could you please speak up?
The commutator that you've got over there, you don't quite have indices conserved. You've got scalar on the right. You've got
Thank you. Thank you very much. Remember I said there had to be a function that depends on the two parameters. Well, now I've explicitly written the function. This is the f of eta epsilon that I was talking about. It's this function. Say again? What these things are? Yeah, I guess I should do that. So, but let me finish, since we're doing this business, which is actually very important. The question was, what's this bracket? And I've now told you the answer is 0. So let me put this in a box. It's true, but only in Minkowski space. And this is now very funny because notice I put this caveat here, and Malik was just telling you that in our universe, there's a cosmological constant. And that means that since this is only true in Minkowski space, because of experiment, I have to really worry and change its mathematics to take into account an experimental observation. We'll worry about that later, but let me just make this very clear. This is true in flat Minkowski space. Something very different is there for one of the two spaces of constant curvature that Malik spoke about. Okay, now, as I said, since we're into this business of talking about commutation relationships, I'll go to the middle set of boards. There's one more bracket that you should ask me to calculate, because I've done Q with Q, I've done Q with P with P, right? Natural one left. So I ought to be able to tell you, if I take a translation with some parameter A and calculate the commutator of that translation with another translation described by parameter B, what is that? Well, it turns out you know the answer to that actually probably since you were about 4 or 5 years old, maybe. And if you're a late learner, probably 6. You can answer that question with a simple physics experiment. Let's coordinatize this floor. I'll call that the x direction. I'll call that the y direction. Now remember, a translation is the actual action of moving something. So I am going to first take a step in the x direction, one step. And I did it to as much as I could comfortably stretch my legs. So I got here. Now I'm going to take one step in the y direction, again, stretching as far as I can. I'm here. I just put a mark on the floor where my feet were. I'm going to go back to where I started. So in that case, I did first x and then y, and I got to where there's a mark on the floor. This time, I'm going to first step as far as I can in the y direction, and now step as far as I can in the x direction. And now mathematically, what do I, by the way, I'm at the same place. So mathematically, what did I just learn from that little tiny experiment? Well, what I learned was, if I take a translation in the x direction, so a translation in x direction means this thing only points in the x direction. So let's see. I'm going to write this as ax p mu. That was my first. I'm sorry. I guess I did the opposite order. I did x first and then y the first time, right? So I did x first, so that corresponds to a mu x dd mu. That was stepping in the x direction. And then I will step in the y direction. And so that would be b. There's some choice of this parameters in the y direction, and dd mu. So this is stepping x, this is stepping y. And then I did it in reverse order. So then I did ax mu d mu, by nu d nu. And I said I got to the same place. What does that mean in terms of a mathematical equation? In terms of these symbols and what they mean? They got to be equal. Otherwise, I'm not in the same place. So it's an experimental fact that these two things are equal. You can go out and do this experiment anytime you want to. Let's move this term to the other side of the equation. it now reads, or rather move this term to the other side, it now reads 0 is equal to ax mu d mu, by nu d nu, commutator. And since the derivatives are, up to some constants of proportionality, also the translation generators, it must therefore follow that p mu, p nu, and this has to be true for all choices of A and B. I should also say that. You're not allowed to do this only for the ones I did. You have to be able to do this for all choices. If it's true for all choices, it tells you that this is 0, and that's the last commutation relationship. Yes, sir?
Can I just ask, how would things be modified in curved space-time?
You can ask. Am I supposed to tell you?
If you can.
I can. Okay. Some of you are adventurous and aren't satisfied with part of the story. Well, Malik talked about some space, what we know about our universe, and that there's this thing called the cosmological constant out there, apparently. Well, in the presence of a cosmological constant, what happens is, oh, by the way, these have to be true for all choices of the parameters, and so these are actually statements about the Q's and P's, not about the A's and B's. And same above. Above, that statement has to be true for of all choices of eta and epsilon, and so you can just erase the eta and epsilons, and the equation must still be valid. Okay, so in the presence of the cosmological constant, something quite interesting happens. The first equation stays the same. Even if there's a cosmological constant, you'll get that same result. The second equation, however, and now I'll drop the parameters and just talk directly in terms of the generators, takes the following form. Cosmological constant must change the algebra. Very weird, but true. And since you forced me to do that, you ought to now ask me, is this true if I'm in a world where there's a cosmological constant? The answer is no, it's not. In a world where there's a cosmological constant, translations don't commute. What do they do? Well, in order to answer that question, I have to tell you about one other thing that I don't know how much of this kind of stuff you've seen before, but I know what I'll do. I'll build on Robert's excellent lecture this morning. So, an excursion into rotations. That's what we'll call this, an excursion. Let's talk about O2, because that's what Robert did in some quite extensive detail over the course of his last two lectures. From these lectures, I would sure hope that you guys would understand things like, what notation were you using for the rotation matrix? A. Yes? Great. In Robert's lecture, he was telling you about this thing called A. It's a rotation matrix. Now, I'm going to write out explicitly a form for A, and the answer turns out to be, if you want to perform a rotation in 2 dimensions, that's what A looks like. That's a rotation through an angle alpha in the xy plane. Okay. Well, if I start with the vector x and y, or rather if I change the vector x and y by the application of A, because remember, translation is always things that do something. So if I take the vector x and y and apply a to it, I get a new vector. So I'll use the prime to say I get something else. But what happens if I pick the angle alpha to be small? Well, hopefully again you say, aha, small parameters means Taylor series expansion again. So all I have to do is know how to Taylor series expand the trig functions. I happen not quite to be so senile that I have forgotten that. And the answer turns out to be for small alpha. So now alpha is, again, we can have alpha very much less than 1. It turns out that a takes the form of 1 minus alpha, alpha, and 1. And if you follow Robert's lecture this morning, I can write this again as 1, 0, 0, 1, 0 plus alpha times 1 minus I, and 0. That should disturb you a little bit because I missed something there. Got to stick a minus I there. And now it works. If you take this out, that's a 0, sorry. Now it works. This thing here, were you using plus or minus signs in your... Use minus? That's what I thought. Okay. So, according to Robert's lecture, this thing is the generator. That's the generator of the translation. Always you can tell a generator because you take the transformation, you look at infinitesimal parameters, you pull out the piece that's proportional to the identity map, and then everything left over proportional to the parameter is the generator. So that's the generator of the rotation. It's this thing. And now that I've got this generator, let me note the following. Let me now do something rather bizarre. Well, you asked for I'm sorry, where are you? Yeah. You asked for this, so you're going to get it. Boy, there's a horrible-looking beast. But I know what it means because I know how to take Taylor series expansions. Because what Taylor series says is that this, whatever this crazy symbol is, it starts off like a 1. And then what Taylor series says is that the next term in the series is whatever you had here. So you write plus alpha times x d dy minus y d dx. And then the next term in the Taylor series is a factor of 1 over 2. I'm sorry, I got the alpha. Is 1 over 2, and then you have to square what was sitting up in the Taylor series. So it's alpha squared times x d dy minus y d dx. And I know how to do this forever. So this thing may look like a fearsome animal, but if you stop and pull it apart, you know how to calculate each step. Now, if I let alpha be an infinitesimal parameter, alpha is infinitesimal, what happens to this expansion? All of this dies. Because when something is infinitesimal, you are never allowed to raise it to more than first power. Right? So, for infinitesimal values of alpha, this animal, this fearsome beast here, for alpha greater than 0 but very small, we find out that the exponential of this thing, alpha x d dy minus y d dx, goes into 1 plus this, alpha times x y d dy minus y d dx. And now that's a horrible animal, but let me use this animal. In Robert's notation, in order to find this prime thing, I just take the matrix and act on this, and that's how I rotate the object. I've now given you a new animal, this thing here. It's a bunch of derivatives, lots of them, but let me apply it to Robert's object x and y and ask what happens. What happens if I do that? Well, And we're only keeping infinitesimal terms. Remember, it's infinitesimal only. So what we find is that x and y, this new vector, is equal to this horrible beast, which we'll write out in its full glory. We're not going to use it, but we'll just keep it in the back of our minds. Is actually equal to, well, because 1 times this thing is this thing. So nothing happened to it. 1 times any object is that object. But now I have to worry about taking this piece here and acting on this. So what happens there? Well, so I have to write it. So I have plus alpha times x dd y minus y ddx. And now I have to act on Robert's object, x and y. But these are partial derivatives. I hope you remember how partial derivatives work. They give you 1 if you differentiate the same variable. They give you 0 if you're differentiating a different variable. And so if you do this calculation really quickly, you will find out that it reads alpha times minus y. X gets put to the bottom. Everybody understand why that happens? I take these set of derivatives and try to act on this. ddx on this produces a 1. But it's multiplied by minus y. So the upper entry gets a minus y put in. What about this first term? Well, this first term has a dy and it's trying to act on an x, so it gives 0. So you only get minus y on top. You do the same logic on the bottom, you find out it replaces x on the bottom. And now the most remarkable thing about this entire discussion was that if you took Robert's A up here for infinitesimal values of alpha, you would find it produces exactly the same result. In other words, again in the language of Robert's discussions, I have found a different representation, a non-matrix representation of the generators of O2. And it's given precisely by this thing. So this thing really is A of alpha, and I think you're using tildes for different representations, right? Okay, so this is another representation. It's the same object. It's the same 2x2 matrix. Oh, I'm sorry. Let me be very clear on this. The generator is an idea. Ideas can be expressed in many different ways. One way to express the idea of a rotation is to write it as a 2x2 matrix. Another way to represent the idea of a rotation is to write this rather ugly-looking animal. Okay? Now, you might wonder what in the world does this have to do with your question? Because your question was how to finish this. And now I am in position to finish it. How am I? Yes, sir.
It appears you didn't write the exponential is operating on xy.
I'm sorry, I didn't write the exponential acting on what?
xy.
On x. Oh, you mean bring this term down?
No, the line x prime, xy prime.
Yeah. Oh, you mean put it here?
Yeah.
Thank you. Of course. At least one person's paying attention in the audience. Now, the reason I wanted to go through all this pain, and he's the guy who forced me to do it, so blame him, don't blame me. But the reason why I wanted to do this is because I wanted you to get used to the idea of seeing this kind of an object. This kind of an object is somehow associated with rotations. In fact, if you've done quantum mechanics, this is no surprise to you, because this is the third component of angular momentum operator, right? It's up to an I and an H bar and all that stuff, but there it is. But we didn't have to do quantum mechanics to get there. It's just calculus. So this thing here is somehow associated with rotations in an XY plane. Well, you know, there was this guy named Albert Einstein, and he gave us this theory of special relativity. And the essence of special relativity is the statement that space and time are not different things. They are all part of one thing. In the same way that on a plane, the x direction and the y direction have no independent meaning by themselves, because you can always take one set of coordinate systems and rotate it slightly, and then what you used to call x now becomes a little bit of y. And that's what Einstein said about space and time, that space and time have exactly the same property, that you can actually take a little piece of something that points in space and make it go into time. or you could take something that only exists in time and make it go into space. That's the essence of special relativity. Now, the way it actually occurs is for Mr. Einstein, what he taught us is that our world is really described by things like this. This is called a four-vector. This is what we mean when we write something like x mu. And when you see calculations involving curvature tensors and all this stuff, this is the basis of these sorts of notations. It's this object that we're talking about. Now, here's the set of coordinates. What do derivatives look like? It's just 1 over c ddt, ddx, ddy, and ddz. So now I know that space-time is the real way our universe works, according to Albert Einstein, and you probably all know that this guy got it right because we're still talking about him. He's the most famous scientist that, well, probably best-known scientist right now. And here's his derivatives. And now, back to the person who asked me the horrible question. In this four-dimensional world, how might I describe the act of rotating space and time into each other? Well, how did I do it to figure out how to rotate x and y into each other? The answer is I went to a very peculiar object to do it, namely this thing. So if I can find the analog of that for space-time, then I know how to, in fact, perform relativistic boost. And the analog of this thing does exist. So let me put a big table here. O2 rotation generator. And what we have is x, let me get all the signs right, x ddy. There's a factor of I here I got to worry about. Minus y ddx. So this is the O2 generator. Uncle Albert comes along and tells us there's this thing called special relativity. It has an invariance group. Robert almost touched on that invariance group today because he taught you about rotations in d dimensions. Well, I'm going to pick d equal to 4 for obvious reason, right? Because there are exactly 4 things there. So d equal 4 is good for me. Now, I'm going to have to do a little bit of a cheat because the thing that Robert proved he was invariant in 3 space, or in 2 space, let me write the invariant. In 2 space, the invariant, or one of the 2 invariants Robert showed you, was x squared plus y squared. That thing, I'll just call it script I, that thing's an invariant. If you rotate that thing, it always gives you the same number. Uncle Albert came along and basically told us the following. He says that there's a group that I can call, let me just put the S there, as Robert was careful to do. There's a group that corresponds to rotating space and time a little bit into each other. And now I have to tell you what's the analog of this generator. Well, in fact, first of all, it turns out there are 6 of them, not just 1. But that's in accord with what Robert told you. Because remember what Robert said was the number, if you have a d-dimensional space, and you ask how many rotations there are, the answer is d times d minus 1 divided by 2. If you're in a space where there are 4 coordinates, d is equal to 4, d minus 1 is equal to 3, so d times d minus 1 is 4 times 3. But you have to divide that by 2, that's 6. So there must be 6 such objects. There are. They look like, they have a name. We use the symbol L mu nu for these 6 objects. And their explicit form looks remarkably similar, which is why I had this entire discussion. To rotations here, there's one subtlety here. Has the Minkowski metric been talked about at all? Minkowski metric? Great. Because the subtlety here is the index here is up. The index here is down. Those are not the same symbol. In fact, the symbol with the down index is the Minkowski metric times the one with the up index. And now I have to find a generator. Now to get back to the long-winded answer to your question. Because the question was, in a space of constant curvature, what's this look like? I can now give you the answer. Let's see. I'm sorry, this is not lambda. This is something called F squared. Looks like this. Translations on a space of constant curvature do not commute. Yes, ma'am? Let me ask Malik one question. In your set of conventions, on a de Sitter space, the non-commutativity of translations has a positive or negative sign.
The commutator with
Two translations. For which space? For de Sitter. Okay, thank you. So therefore, let's see, for de Sitter, it would be positive. Therefore, the answer turns out to be this. And the answer to your question is yes. This thing here is the cosmological constant. So that's what happens when you push me in such weird directions. Yes. If you push me to discuss spaces of non-constant curvature, which I am prepared to do, then we get into the discussion of a theory called supergravity. And that, let me see, there's some experts here in the audience about supergravity. They can tell you that's a piece of hurt you don't want to deal with. It is incredibly complicated, and I cannot do it justice in a short amount of time. So given the tools I have now, this is all I'm capable of discussing. Yes, ma'am?
But you can do the F from GR proofs without their conventions.
I'm sorry, you can determine the S.
Yeah, when you know if you come to between
Experimentally, I can, by the same presentation that just went before mine, I can measure this thing. Right? Okay. So that's what happens when you try to think about supersymmetry on a space of constant curvature. It turns out that things get a little bit more complicated, and the cosmological constant, at least its square root, which is this thing F, sneaks into the equation. By the way, this was first discovered by a physicist named Ferrara. Yes, I'm sorry, I saw a hand. Yes?
Curved space with no cosmological constant.
Then, as I said, you will then force me to go into something called supergravity. If you want any space more complicated than the ones I have discussed, I must teach you something about supergravity. Yes, ma'am?
It's not a purely classical effect anymore. It's already contained supersymmetry.
Yeah, that's one of the weird things about it. It's already you believe in supersymmetry, it's already sort of there. And so supersymmetry is a very strange symmetry. And because of this, by the way, you should begin to suspect that supersymmetry is somehow very intimately related to the structure of space-time. Because here's a symmetry that knows whether you're on a space of no curvature and no cosmological constant, Minkowski space, but when you're on a space of constant curvature, this symmetry perforce changes. So it knows. Therefore, supersymmetry, from the very beginning that supersymmetry was discovered, people suspected that this symmetry had some extremely deep relation with space-time symmetries because of these things can't be accidents. That's the point. Okay. Well, we now have a working set of definitions to understand what is supersymmetry, either on Minkowski space or in the more complicated case of, and let me point out, by the way, that this minus sign is here. That means anti-de Sitter. And in Malik's lecture, he sort of gave you three cases. If you looked very carefully and watched this, in fact, I guess he used big lambda, in fact, to try to be consistent notation. He gave you three cases to consider for lambda. He said lambda could be 0, it could be a positive number, or it could be a negative number. I've discussed two of those three examples. I've discussed 0. If you look at this, because f is a number, oh, by the way, I should be really careful. It's actually the absolute value of f that occurs here. So I should be very careful to tell you that. Now, I guess since it's squared, it doesn't matter. But the point is that it might be complex. So if you put some complex number here, then the absolute value would be important to show up here. Because a complex number is actually allowed. Okay, so what's interesting about this is you see that, I'm coming up on time. Okay, is that only the anti-de Sitter case occurred here. What about the de Sitter case when the cosmological constant is positive? Because, in fact, that's the universe we live in. The experimental evidence from type 2 supernovae tell us that our universe is one where the cosmological constant is small but positive. Well, here's some real bad news, folks. Supersymmetry is inconsistent with the kind of supersymmetry we've talked about, and the simplest mechanisms, is inconsistent with de Sitter geometries. But that's the universe we live in. So perhaps all of this work on supersymmetry is irrelevant. Maybe it has nothing to do with our universe. It is the greatest challenge to people who believe in superstrings and what have you to find a way out of this conundrum. Jeff, your hand went up. Oh, you might do that. You might indeed do that. But those of us who have invested our entire careers, if we catch you in a dark street, might decide to make some adjustments in your anatomy. But look, logically, yes, you could throw supersymmetry out the window. And by the way, this is the end of my presentation. So, Sir Chairman, this is the end of the presentation. So if there's some, if we could go into some Q&A, then I think I'm actually doing that by trying to get back to this point. So the point is, yes, logically, you could throw supersymmetry out the window. The only reason why you might be tempted not to do that is because superstrings are the only consistent way that we can conceivably think of a quantum gravity theory. Well, there's a few folks who have something they call loop gravity, but if you studied loop gravity, you might have some doubts. But I'll let Don, is Don still here? Yeah, maybe you can tell folks about loop gravity, or maybe John, you want to say? Fine, exactly. So there's another point of view. There's those of us who are a lot of us who are big aficionados in string theory think of the loop gravitist as a communist, and so we're waiting for that. We're waiting for that to not work, actually. But there's a healthy disagreement, shall we say? But if you, like a lot of us have prejudices that there's something fundamentally unsettling about loop gravity, then superstring theory is the only tool we have for trying to reconcile quantum and GR. So we might not want to throw it away.
There is, of course, the other possibility, which is that loop gravity is another piece of the story we haven't yet understood.
Of course.
We should wait and see.
That's why it says healthy disagreement.
Give everyone a chance.
Yes.
There's enough room for everyone to try different approaches.
Yes.
Okay. Let's thank Jim for his excellent lecture. Let's have a few more questions. Just a few more, because we actually have to start something at 5. But let's just have a few more questions. If there are any, of course, we could break this point. There's a question.
Yeah, I have quite a technical question. The f of derivative, what does it depend on? How do you calculate it? And
What does what depend on?
the f, the function f. Is it a function? Is it a...
It's a constant. I keep saying space of constant curvature. I keep saying that over and over again. A space of constant curvature. I said that now 5 times.
Does it depend on the
What fixes it?
Ah!
That's what she's asking.
We don't, there is no first principles determination of this parameter. It's like what fixes the mass of the electron in Dirac's theory. Answer, experiment. Same thing.
Okay, one more question.
Yes, sir.
Undetermined parameters in theory.
In what?
F, for example, if there's no first principles fixing of it, then it's an undetermined parameter.
Yes.
Put in by whatever.
Yes. How many others are there? It's the only one. At the level of the algebra, which is what we've just gone through, it's the only one. Okay, well, oh, I'm sorry. Yes, sir.
Going back to when we've got two supersymmetry changes.
Yes.
Now, effectively, if we've taken two different routes of doing it, we get a translation. Is that as putting some sort of fuzziness?
Is that putting some sort of fuzziness? That's a very good question. And in some sense, yes. In some sense, an alternate interpretation of supersymmetry is that there's a kind of weird mathematical fuzziness around points, and that somehow these parameters, these things here, are somehow a characterization of that fuzziness. Tomorrow we're going to see it even gets worse, because these parameters will turn out not to even be numbers. And I'll explain that tomorrow.